The next point that we are going to observe is your equatorial point. So we have dipole, we have a line connecting the dipole. Say this is the center, and through the center we have a perpendicular line, and a dot on this line is your equatorial point. And this is known as your central axis or plane of symmetry, because to the left and to the right it looks similar. That's why this is known as plane of symmetry. So what is the electrical field over here? As you can see, we saw what's the electrical field along what? Along your axial point. Now we're looking at equatorial point. So observe the dipole. So the equatorial point now. Clearly the direction of electrical field lines along the equatorial point is in the direction of dipole moment or opposite? Yes, it's opposite. Okay. We'll observe that, of course. So let's see this. I have the diagram already. So we have the negative, positive, and your direction of dipole would be where? Yes, it would be so. Agree? So wherein we have right and up to be positive. Now this is your center. So this length will be A, this length will be A, this is 90 degree. And now we have a point on the equatorial point. Let's call OP as our units. And we will make use of this line. So let me draw this, because we will observe how minus Q affects a charge at P and plus Q affects the charge at P. Now we have a push force, right? Plus Q. If there is a unit charge over here, it will push it. And the charge is unit positive charge and it will pull it, minus Q. Agree, guys? So this is what is happening. So this is because of minus Q and this is because of plus Q. Next, what else we need? For now, this is all that we need, I guess. Let OP. Oh yeah, actually we need to write a big fat statement over here. I forgot. Let me do that. Yes. So we have to consider a dipole with charge plus Q and minus Q separated by a distance of 2a and placed in vacuum. Now let's have the point P on the equatorial line at a distance of r from the center O of the dipole. Okay. And what else? I think that's good enough. So next thing is, yeah, I think this is good enough. The free body diagram of a unit positive charge P at P. So we have a dot and we have this line that of course we'll use. So what are these lines? Actually, let me do it over here. That's more convenient. So this is your parallel and perpendicular lines to your dipole moment, for example. So this would be your electrical field. One is a push, another is a pull. think that's good enough. Now we need to resolve it. For resolving it, we need angle. Agree. So which angle are we looking at? We are looking at this angle and somewhere there. But it has to be related to the diagram. So which point or which angle should we consider in this space? Yes, it makes sense to consider next to the dipole, right? So here, this is alternative interior angles. Then this between these two angles, which can we find? Well, this angle is 90 minus theta for obvious reason, angle sum property. This is opposite to that. And so this has to be theta. Make sense? So basically, this is theta and this is theta. So when we resolve force, this length is your sine theta and this length is your cos theta. This length is your sine theta and because of this length is your cos theta. So this will add up 2 times. So this will be E plus E minus. So this is E minus Q. This is opposite, so sine theta. This is opposite, so this is also sine theta, right? When you resolve it. And this is cos theta because they're neighbors. And this is cos theta. So for people who find this confusing, I'm just doing this for you guys. So this is your right angle triangle. Agree? Now, opposite is what? Opposite is this. This is your opposite side. So this is nothing but your opposite and this is your hypotenuse. And so when you resolve it, this will become EQ sine theta. And so the length over here will get EQ sine theta, E minus Q sine theta at the bottom. Here we are taking right and up as positive, remember. Does it make sense? Right and up as positive, and so left is negative, down is negative. So therefore, the net electric field at P would look like E net or EP will be equal to minus E minus Q cos theta I cap or P cap in this case. Right, it's opposite to that of your, let me go with this. This is positive and this is positive, so anything to the left is negative. So this 2 is negative, so this 2 will add up. While up is positive, down is negative, so this 2 will correct, subtract. Agree guys? And in this case, the magnitude of these two set of charges is positive, right? And from this, what can we tell? Therefore, this result will be minus 2 times of E minus Q cos theta I cap. Okay, so let me make some space. Now, so of course, this is not the final answer. We need to express in terms of, one is of course A, P cap, then R, and Q as well. And Q as well. Now, how will we do this? So, we have, first is minus Q. 1 by 4 pi epsilon naught, the source charge divided by the length. Here the length is L square. That's what I've taken. Of course, we need to re-express L square also. L square will be, let me show the diagram. What I mean, this is your L. Let AP and BP be equal to L unit. Now we need to express L in terms of A and R. So obviously it is A square plus L square. Square, my bad, not L square. L square is equal to this. And so we have, yeah, 1 by 4 pi epsilon naught Q divided by A square plus R square, the whole square. Oh, sorry, Pythagoras theorem. Now, next term we can go with this cos of theta. Cos theta is adjacent. Theta is over here. Adjacent is this. Opposite hypotenuse is that. So A by L and A by A square plus R square to the power of 0.5. Finally, we have I cap, which is equal to P cap. Right? I cap and P cap in our diagram is one and the same. Again, for your diagram, it might be opposite. For my diagram, it is the same. So whatever you do, you will get the right answer. So let's substitute it in 1. So we'll call this as 1. So what do you end up with? Field at point P will be equal to minus 2 times of, yes. So we have 1 by 4 pi epsilon naught Q by A square plus R square. And here it's A, so I'm writing A here. And the power is 0.5 and this is 1. So this will be 1.5. Again, I'm doing the math directly. And of course, we have P cap. Instead of I forgot I over here. Or I've written. Right? And finally, we're going to substitute P, which is 2 times of A R. So when we do that, we have minus P by 4 pi epsilon naught 1 by A square plus R square to the power of 1.5 P cap. So what is it? The math is telling it is opposite. What is opposite? Electrical field lines are opposite to that of dipole. Right? Dipole moment is from negative to positive while the fields are going from positive to negative. Along the equatorial point, can you see that? And finally, let's talk about a case wherein we have the distance is very, very far away from the dipole in comparison to the length of the dipole itself. So what happens? From this, we can infer that A square plus R square will be approximately equal to R square or A square. Correct, R square, is it not? So we have this minus B by 4 pi epsilon naught. What will happen to denominator? If this is R square and this will be R cube. And from this we can infer what? Therefore, field strength reduces at the rate of 1 by R cube. So similar set of conclusion was made and been told, so on and so forth. Now, let's compare. So when it came to your equatorial point and axial point, what's the difference? At axial, we have the direction to be same as that of dipole. Here it is opposite. That's the very first thing that I can remember. Then what else? Then anything else that we can actually compare? Yeah, this is 2 times and all of that. So it's kind of stronger, right? So this would be 2 times that of strength in terms of strength. At axial, it's double the strength. Then what else? These are the 2 things. Let me see if there is anything else. Yeah, guys, these are the 2 points. So there's a small note over here at short distance. Actually, even for long distance, it's the same. Anyways, okay. Right, guys. So this is a difference. You may get it in various forms. MCQs, reasoning, so on and so forth. So what is that we looked at? We have dipoles. Dipole have a line connecting them, and we saw what happens to the electrical field along the dipole length. Now we're looking at equatorial point. The central axis which divides the dipole into 2 similar structure. So all we did here was quite simple. We drew a good diagram. We named all the things that is needed, including angle. And then we started with the statement. So again, typo error, point. And we consider point P along the equatorial line. And then we resolve the vector, in this case electrical field, at that point. When you resolve it, the up and the down gets cancelled and things will be opposite to that of dipole moment. And all we did was add them vectorially. This is as per superposition theorem. And finally, we need to express all of these terms in terms of A, dipole moment, R, and Q. Right? Unit vector is equal to I, cos theta is equal to this expression, so on and so forth. Quite simple. When you substitute it, you end up with a pattern that is 2AR is equal to P, and so we have P, the magnitude of the dipole moment. You can express in that term, and that's your derivation. And we have a small conclusion that for very far region, the dipole moment reduces at the rate of cube of its distance. And a small conclusion or comparison between axial and equatorial. So in terms of direction, it's same as P and opposite of P and so on and so forth. Strength wise, along the axial line, it is a lot stronger. And that's it. So you can pause and have a look.